Okay, in this lesson, we're going to learn about Taylor series and Maclaurin series. So, starting off at the top, it says Taylor polynomials can be used to approximate other elementary functions such as sine of x, e to the x, and the natural log of x. All right, let's look at an example of a sine of x problem. So it says find the equation for the tangent line for f of x equals sine of x at x equals 0, then use it to approximate sine of 0.2. So they ask us to find the equation of a tangent line. All right, so let's start there. So equation of a tangent line, we've got y minus y1 equals some slope times x minus x1. All right, so going back to point slope form, equations of tangent lines from when we first learned derivatives, way back in AB. So we need a point and we need our slope. So they give us that the x value is 0. So that is our x1. Plugging that into our sine function, we're going to get our y1. Sine of 0 is 0. So there's our y1. Plugging those into our point slope form so far. Y minus 0 is just y. X minus 0 is just x. So we're down to y equals m times x. And now we just need to find our m. Remember, that's our slope. To find our slope, we look at the derivative, the instantaneous rate of change. So f prime of sine of x. Derivative of sine is cosine. Okay, and we're looking specifically at, let's see, our center. Okay, so it says our center is at 0, 0. So the slope right there at 0, 0 is going to be f prime of 0, which is the cosine of 0, which is 1. All right, so that means our slope is 1. So that means our tangent line is just y equals x, all right, or 1 times x. All right, so there is our approximator. Okay, so sine of x is approximately y equals x around that point. We want to approximate sine of 0.2. All right, we're going to use this model to approximate sine of 0.2. If we put 0.2 into our model, well, y is the same as x. It's going to spit that 0.2 right back out at us. All right, so that's our model's approximation. Boom, we got our approximation. The last part says, is this an over or under approximation of the sine of 0.2? So we can do this a couple different ways. We can say, all right, so using some more calculus, if we look at the second derivative and use our second derivative test, derivative of cosine is the opposite of sine of x. And then if we look at it at that point, 0.2, I don't know exactly what it's going to be, but 0.2 sine is going to be positive, so the opposite of that is going to be negative. If it's less than 0, that means it's going to be concave down. If it's concave down, then our linear approximation is going to be an over approximation. Okay, if we want to look at it graphically, then here's our sine function. I've already put some of this into Desmos. Here's our center, 0, 0. We're looking at approximating this point here. So here's the actual point at 0.2 comma whatever the sine of 0.2 is. Here's our model, y equals x. Remember, this is only meant to be good for values. Whoops. Values close to 0. All right, and then here's our prediction on our line. All right, and you see how that linear function is a good predictor, but only for right in this area in here. Anywhere outside of that, it diverges from the actual sine function and is not a good predictor. But in close here, we zoom in closer and closer, then we can see that that linear function in orange there, which is our predictor, is slightly over predicting that actual value at 0.2. All right, always good to have a visual to go along with what we're doing on paper. All right, so the equation of the tangent line using example 1 is called a first degree Taylor polynomial. Ooh, so we just found our first Taylor polynomial right here. That y equals x. It's our first Taylor polynomial. It's a monomial. We're not typically going to use monomials, and we'll see why in just a second. Taylor polynomials of higher degree can be used to obtain increasingly better approximations of non-polynomial functions with a certain radius from a center of approximation x equals c. So they're saying that, kind of like with those power series that that you looked at recently, if we put in more and more terms and get higher and higher degrees in our polynomial, then we'll get an increasingly better approximation of a non-polynomial function, like a sine or a exponential or a log function. All right, so definition of an nth degree Taylor polynomial. If f has n derivatives of x equals c, then the polynomial p sub n of x equals f of c plus f prime of c times x minus c plus f double prime of c over 2 factorial times difference of x and c squared plus so on and so forth. And our rule is f to the n, but let's be careful here. Ooh, what just happened? Lost control. All right, this n here is not an exponent. Okay, this is our nth derivative. All right, so recall when we do higher order derivatives, we start with these tick marks, these hash marks, for our first, second, third. But then after third, the tick marks get out of hand, and we just put our nth derivative, whatever that n is, in parentheses. Fourth derivative, put a 4. Fifth, put a 5, so on and so forth. All right, so here's our rule. F to the nth derivative of f times of c over n factorial times x minus c to the nth power. All right, this n here is a power. All right, that is called the nth degree Taylor polynomial for f centered at c. Note, a first degree Taylor polynomial is a tangent line to f at c. That's what we just had back in example number 1. Also note, f to the nth derivative of c over n factorial is the coefficient of the x minus c to the n term. All right, so note note that this part here, and this part here are all just coefficients of that x minus c to the nth power term. Okay, a lot of symbols, a lot of notation. As you do more of these together with me, and also try some on your own, the more the notation gets clearer. Because I'm sure right now it might be like, holy moly, that's a lot. It's a little overwhelming. Let's look at the simplest type of a Taylor polynomial. All right, it's called a Maclaurin polynomial. All right, the nice part about a Maclaurin polynomial is that the center is always 0. All right, it's a type of a Taylor polynomial where the center is always 0. Okay, and that's what we got here. So the only difference is instead of x minus c, same thing. It's just x minus 0 or just x. And so those parentheses have just been cleaned up a bit. So let's look at using a Maclaurin polynomial. All right, example 3 says, I don't know where example 2 is. It says find the Maclaurin polynomial of degree n equals 7 for f of x equals sine of x. Then use p sub 7 of x to approximate the value of sine of 0.1 using the correct notation. Find the error for your approximation. All right. So when it says use p sub 7 and a polynomial of degree n equals 7, then that means we're going to need to find not 7 terms necessarily, but out to the 7th degree term, all right, or the monomial with a degree of 7. That means we're going to have to take a lot of derivatives. So let's find those derivatives first because we're going to need them in our coefficients each time. All right, we're going to need those derivatives at center equals 0 because, again, Maclaurin polynomial, when we see that, we know that our center is at 0 of our model. All right, so let's do that. So we know our initial function is sine of x. Derivative of that is cosine of x. Derivative of that is opposite of the sine of x. And so on and so forth. All right, start to see a pattern. We kind of loop back around when we get to the fourth one. All right, and we don't want just those functions. We want those functions evaluated at the center. All right, our center is 0. So I'm going to try to squeeze this in here for x equals 0. And let's evaluate each one of those. All right, so, all right, again, because in our Maclaurin series, we are evaluating our function, its derivative, and so on when our center is input into that function, not just those derivatives themselves. So sine of 0 is 0. Cosine of 0 is 1. 0. The opposite of 1, 0. You see a pattern. 1. Opposite of 0 is just 0. Opposite of 1, opposite of 1. Okay, so we've got all of our derivatives there. So let's build out our p sub 7. All right, so first term, again, we're following this as our guide here. All right, it's just plugging in our value, our center, into our original function. So plugging in 0 into sine of 0, we get 0. All right, now we're looking at the first derivative. That's that 1 right here. So 1. And then it doesn't show it here, but to follow the pattern, I like to kind of show the pattern. We're going to be dividing by n factorial. All right, so we're really dividing by 1 factorial here. And I like to just write that to remind myself that's the pattern of things to come. All right, and then times x. All right, going to our next term. All right, we're looking at the second derivative for x equals 0. So we get 0 over 2 factorial times x squared plus, and then go into our next one, we have a negative 1. So negative 1 over 3 factorial times x cubed. And keeping going on with our list, next one is 0 over 4 factorial. And again, this is n equals 0, n equals 1, n equals 2, n equals 3, n equals 4, and so on. We're going out to n equals 7. Oops, forgot my x here. All right, when we hit that 7th degree polynomial, we can stop. And that is our p sub 7. Although, if you notice, there's a lot of 0 terms in there. We want to remove those. All right, so let's rewrite it with those terms taken out. And again, this is our approximation for sine of x. So we can say sine of x is approximately our 7th degree Maclaurin polynomial. Again, that doesn't mean that it's got 7 terms. We just go out to the term with the 7th degree, all right? Because this one's just a 0. We don't need to write that. 1 over 1 factorial is just 1 times x. 0 times whatever is just 0. Here's a negative here, so minus 1 times, we're going to go ahead and put that x cubed up in the numerator, over 3 factorial. I'll leave them as factorials for now. It'll help us to see the rule in just a moment. This is a 0. We don't need that. I'll go ahead and cross out the other 0 term there. So our next term we're going to keep is plus 1 times x to the 5th over 5 factorial. And then that last term is minus x to the 7th over 7 factorial. All right, boom, there's our p sub 7. That is going to be our approximation function that we're going to use to approximate the sine of x. So they want us to use it to find, evaluate a value of sine of 0.1. All right, so let's do that. So sine of 0.1 is approximately, if we were to plug in 0.1 into our function here, that's definitely going to require a calculator. And if you plug that into your calculator, you're going to get 0.0998. Going out 4 digits just because. Boom, and that's our approximation. All right, it says find the error for our approximation. Well, the error is the difference from the actual to the approximate. So we need to find the actual. So the actual sine of 0.1, all right, out to those 4 digits. If you put that in your calculator and you're in the right mode, radians, then it looks the same, all right? It looks exactly the same. So this is a pretty good prediction. It asks us to find the error. So let's go to our calculator. All right, let's also get a visual for this. All right, so let's see. Let me get rid of, we don't need those anymore. We still need our sine of x. There's our function there. Let's see. What have we got? There's our point. 0.1. .1 comma whatever sine of 0.1 actually is at 0.998. That value right there. All right, so see how Desmos goes out to, if you count these, there's 13 digits to the right of the decimal. So here is, I'm going to kind of build this, type it in and build it. Here's that, that tangent line to that point at 0. We want to add in more and more to get a better approximation. And let's see, let's go ahead and zoom in a little bit. Okay, so my next term was minus x cubed over 3 factorial. What happened? All right, there we are. All right, so you can see how that approximation, that Taylor polynomial in green, is a little bit better of an approximation. Here's, let's see, where's my point? There's that prediction point. Here's the actual point. Again, it's hard to see. If we zoom in a little bit, and we'll see that is a really good approximation around that point there. And it kind of breaks off just outside of 1 and -1. Let's go further. We've got, we did our piece of 7, so let's keep going. All right, x to the 5th power over 5 factorial is even better of an approximation. You can see it goes out past the 1s. It's still looking good a little bit. All right, and then our last term, x to the 7th over 7 factorial. All right, there's our actual Taylor polynomial that we just found. And we can see, again, goes out a little bit further. That radius of convergence tends to be better. It goes out, widens a little bit further. And we'll see that the actual prediction is even better itself within that range there. And if we keep on zooming in and keep on zooming in, then we can't even tell the difference between those two. All right, that's how good of a prediction this model is. All right, you can see the scale. X scale at the bottom. Desmos kind of gave up on, there's the Y scale a little bit. It's going out to 5 digits past the decimal. All right, and it's still, I can't see a difference here. I could do this all day. And Desmos has given up. All right, that's as far as it'll go. Won't even let me move it. Still can't tell the difference. All right, that's how close it is. And check out the digits. The digits out to 13 digits past the decimal are still the same. Still the same. Our calculator can't even tell the difference between those two. So, how are we going to write that? We can say our error is less than 13 digits is 1/10 trillionth. All right, if you count tenth, hundreds, thousands, 10,000s, 100,000s, and so on, 13 digits is 1/10 trillionth. All right, pretty good approximation, if you ask me. All right, one more problem. Example 4 says list the first four non-zero terms and the nth term for the Maclaurin series for f of x equals sine of x. So that's the same function we were just doing. We've got those 4 terms there. So let's just copy those down. So we have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Those are the first 4 terms. It says also find the nth term. Okay, so plus minus so on and so forth until we get to that nth term. All right, so here comes in our writing a rule from a list. If this is n equals 0, 1, 2, 3. Then our rule is it's alternating, so we've got a little alternator in there to the nth power, and that lines up. -1 to the 0 is positive, so that one's positive. All right, and then our numerator is times x to the, and those are all odd numbers, 1, 3, 5, 7. So 2n, that's going to be a +1. That takes care of our numerator. Our denominator is just that same value, but factorial. Okay, so that's our nth term. So if we were to write this as an infinite series, then our sum n equals 0 to infinity of that rule would give us our Maclaurin series, infinite Maclaurin series, to approximate f of x equals the sine of x. All right, in the next part, we'll look at a couple of more Maclaurin series examples and get into some Taylor series where our center is not 0.